Disruptive Technologies at FISITA World Automotive Congress 2018. The chairman of this session would be Mr. V Raman, Senior Executive Director, Maruti Suzuki India Ltd. And we have two speakers, Dr. Azim Eskandarian, Virginia Tech USA, to speak on the topic autonomous mobility, and Dr. Anand Gopalan, Chief Technology Officer, Velodyne Lidar, on autonomous mobility. And it's my great honor to introduce the chairman of this session, who doesn't require introduction. Mr. V Raman is a graduate from Delhi College of Engineering with BE in Mechanical Engineering. Prior to joining Maruti Udyog Limited in 1984, he worked with Escorts Yamaha Division Limited. Mr. Raman started his career in Maruti in vendor development department. During his tenure in vendor development till 2001, he was responsible for component and supplier development. His key achievements were development of the supplier ecosystem and also their upgradation of quality and technology by enabling tie-ups and joint ventures with global auto component suppliers. Mr. V Raman currently heads the engineering vertical of Maruti Suzuki. Raman was instrumental in developing Maruti Suzuki engineering into a R&D hub of Suzuki Motor Corporation outside of Japan. During his tenure, many successful new models were launched. Key achievement under his leadership were the design and development of highly acclaimed compact SUV Vitara, Brezza, and setting up of the state-of-the-art R&D center at Rohtak. Mr. V Raman is also active in various professional bodies as Vice President of ARAI Governing Council, Chairman of SIAM Committee on Emission and Conservation, Member of Governing Council of National Institute of Design, Director in Bharat Seats Limited and Krishna Maruti Limited, Chairman of SAE India Supra and Governing Board Member of SAE Northern India Section. And he is also active member of various CIA committees on design, on technology, on quality. For his outstanding contribution to automotive R&D and the successful Vitara Brezza, Raman was awarded Man of the Year by Top Gear in 2017. He was also the recipient of Engineering Excellence Award by SAE India Foundation. Ladies and gentlemen, let's give a big round of applause to Mr. Raman, and may I request Mr. Raman to take this panel discussion.
Good afternoon, friends. Welcome to the plenary on disruptive technologies. And it's always a challenge to have a plenary session post the lunch. But I'm sure our esteemed speakers here would ensure that all of you are given a lot of food for thought as far as this disruptive technology is concerned. So before I introduce the speakers, a brief statement from my side. I think this is one of the ACEs which we always talk about, and that is autonomous, and both the speakers here are going to talk about autonomous mobility. But one of the key things in autonomous is that how do you make vehicles safer? And just to get the context and get the Indian context, I'll just quote certain data. And there was a study done by Terry, and that said that 23% of Indians walk, 13% commute by bicycle, 13% commute by two-wheelers and mopeds, 11% by buses, and just 3% by four-wheelers, and about another 3% by three-wheelers and taxis. So that's what the mobility situation in India is. So one would look at it as an opportunity. We are at 20 cars per 1,000. USA is at about 800. So I think that's a lot of opportunity. India is rapidly urbanizing, and there are a lot of challenges and opportunities also. And mobility is going to be one thing which is going to be a common thread, which is going to be part of this urbanization. Friends, the UN Decade of Action for Road Safety for 2011 to 2020 has 5 pillars, and that is road design and infrastructure, user behavior, road safety management, trauma care, and making vehicles safer. And we, as part of the mobility industry, are looking at making vehicles safer. So now if you look at the accident statistics of India, this recent 2-year back study of the Ministry of Road Transport suggested that the two-wheelers are the major contributors in the accidents. And two-wheelers is 34%, four-wheelers is 24%, and trucks is about 21%. And India has got the highest accident rate, and in terms of fatalities too, India leads in number of fatalities. And if you look at fatalities, again, two-wheelers is 35%, and four-wheelers is 18%, and trucks is 11%. So if you see what does this all mean, it means that there is, the cause of accidents is something which we need to study further. And if you look at that, driver fault is coming out to be 84%. But the data is something which is very, very, it's not very discrete. I mean, you don't have too much detail because the accident analysis data in India is not so robust. But that's what the numbers suggest, that driver fault is 84%. And out of that, 66% is because of overspeeding. We at Maruti Suzuki did a small survey, and now I'm talking about user behavior. And that suggested that the front seat belt usage in India is 29%. And the rear seat belt usage in India is just 4%. So what does this mean? That people do not understand safety, and the consciousness towards safety is something which is not there in India. And that's something which we need to educate customers and the people at large, that safety is something which is very, very important. So having said that, what are we trying to do? And we are trying to make sure that the perception of the driver, okay, and the response of the driver in terms of sense, detection, in terms of what he does, what he plans to do as a maneuver, and when he wants to accelerate, when he wants to brake, or when he wants to steer, that is something which is the perception and the sense of the driver. And the vehicle is going to perform in terms of vehicle dynamics, and the actual vehicle will perform in terms of trajectory. So autonomous is something, this combination of both these, and trying to make it more, perceptible and make it more, and that's, I think, what the subject matter experts will talk about today. What we are going to do here is quickly, I'll introduce the speakers, and we have about 20 minutes each for the speaker, and then we'll have about 10-12 minutes for interaction with all of you. So my first speaker is Dr. Azim Eskandarian. He's from Iran, and he is the professor and head of mechanical engineering in Virginia Tech since August 2015. He became the Nicholas Rebecca Deschamps Chair in April 2018. He established the Autonomous System and Intelligent Machine Laboratory at Virginia Tech. And he has over 165 publications, 60 referred journals, and 99 conference articles. And of course, he has a handbook of intelligent vehicles. And because of the popular demand, it has been translated into Chinese in 2014. Dr. Eskandarian is a fellow of ASME, senior member of IEEE, and a member of SAE professional societies. So welcome, Azim. And before I call you up, I'll like to introduce Gopalan also. Dr. Anand Gopalan is the second speaker I have on the panel today. He's Chief Technology Officer of Velodyne Lidar, and he's responsible for all technology and advanced product development at Velodyne. And he's a seasoned semiconductor executive with experience and leading worldwide engineering organizations for development of consumer networking and enterprise domains. And he has grown and managed organizations through deep and dynamic business model transitions. Anand has come to Velodyne from Rambus, where he was the VP of engineering, responsible for all chip and IP development. for the memory and interface divisions. And Anand holds a BE in electronics from Mumbai University, as well as a MS and PhD from Rochester Institute of Technology and Electrical Engineering and Microsystems Engineering. So welcome, Gopalan, to you too. And now I request the first speaker, Dr. Azim, to come up to the stage. Thank you.
Good afternoon, everyone. Good afternoon, everyone. Wow, that's much better. After 30 years of doing this in academia and in industry, I don't know which one is worse, being the last speaker of the conference or the one right after lunch. So I don't know, because everybody has enjoyed lunch. Let me start by first thanking the organizers and our session chair. It's a pleasure and honor to be here and travel to India for this particular conference, which is very impressive, well-organized conference. Let me start by a question, because my profession is a professor. So how many people do you think have died since yesterday in automobile crashes? 3,400. So when we were enjoying ourselves here, 3,400 people died in car crashes. So that's why I dedicated my career to vehicle safety. So I will go over some significant numbers on that particular area, talk about integrated safety, a few examples of our humble research in my own laboratory, just the current one, not the past one, because the past will take a long time. We have only 15 minutes for this. So, and a few perspective on mobility and the direction that I think would be helpful for this community that is interested in automotive area. So in the United States, annually, current statistics is about 37,000 fatalities in about 34,000 crashes. And that's about 102 people dying per day. If you put numbers to it with respect to airplane crashes, you know, it's about 200 passengers in an airplane on average, and there would be one every 2 days. So if somebody asks you, would you get on a plane if there was one crash in the news on an airplane every 2 days, would you ride a plane or not? Most of us would say no, but we still get into our cars and drive. So it is the safety, the significance of safety is very important. Each year, about 1.25 million fatalities happen around the road, around the world on the road, and that's equivalent to about 3,400 people killed in road crashes the past 24 hours. If you look at the World Health Organization data, the leading cause of death for people at age 15 to 29, young people, is really no other disease but car crashes. And half of those that die in these roads are pedestrians and bicyclists and motorcyclists. So it is a very important, alarming statistics once you review it. The cost is also enormous. So the insurance cost, the loss of, you can't put value to the loss of life, but the economic loss is huge. So that all justifies to pay more attention to vehicle safety than maybe we have done in the past. Now, US is not doing that great relative to other Western countries. Sweden probably has the best statistics in terms of slowing down the number of fatalities and injuries. The US is, all the trend in major Western countries is going downwards, but because of the more vehicle-driven, mileage-driven, then the data is still alarming. So what do we look when you look at the accident sequence? You see different phases with your normative driving, and then range where danger phase presents itself. Then you get to a crash unavoidable temporal phase, and then a crash happens, and finally, post-crash, you have to get the proper care to the people who were injured. So my work, initially I worked a lot on during the impacts of the passive safety crash worthiness, whether it is the airbag deployment or belt design or crush zone design. We worked extensively with finite element simulation in academia, which was helpful to both government and industry. But then I moved on to, we reached a plateau in what we can accomplish by crash worthiness. So ultimately, the best way is to avoid crashes altogether. So we worked a lot on the pre-crash safety and active safety systems. This is an example of my earlier work with some of my colleagues where we actually reverse engineer vehicles with finite element. Many of you from auto industry and suppliers are very familiar with that. I saw Faro arms in the exhibits. We used Faro arms extensively for reverse engineering vehicles, and then moved on to dummy and occupant modeling and other applications of finite element for design of roadside hardwares as well as vehicles. Then we moved on analyzing what is the contributing factors to crashes and how we can avoid them altogether for the target of 0 fatalities. So these were a study that was done. You see a lot of the quotes about autonomy nowadays that 94% of the cause of the crashes are by the human, but this study was done maybe more than 20 years ago by NHTSA. It's called tri-level study that looked at the 3 elements of human, environment, and the vehicle itself. And you see the vehicle is the least of the flaws in accidents or crashes. And human has the major role. So another question to you, if you were to put your money in investing to minimize crashes, where would you invest? Which column? First column, right? So that's where the most error is happening. Therefore, your investment or attention should be mostly on that area. And that generates all the ADAS or driver assistance systems and what we're moving towards nowadays, which is the driverless and autonomous vehicles. That means totally remove that element from the equation, therefore minimizing the accidents and minimizing the fatalities and injuries, which would have a tremendous effect if you really had 100% driverless autonomous vehicles. I don't know how many of you are in this field, but the SAE has a standard for the purpose of autonomy, which has 5 different levels, actually 6 levels from 0 to 5, 0 being the total manual driving, and level 5 being totally hands-off and total system driving. Without getting into too much detail on specifics on each one of them, a lot of the driver assistance happens in the level 1, 2, and even some in level 3, but then 3, 4, and 5 are really moving towards autonomy. So the thick line that you see on the plot is really dividing where the human has a role versus the system, which is the vehicle itself. Now, if you look at the driving, a simple driving scenario is where you have a desired trajectory, you're trying to maintain that trajectory, you perceive, you sense, you detect, plan, decide, and then there are 3 control actions that you do: accelerate, brake, and steer. So that's the driver role and the vehicle role. So if you want to move on to autonomy or collision avoidance, that's where your actions are. If you want to replace things on the vehicle, those vehicle dynamics issues that you have to handle and deal with. And then the driver side is the brain of the whole function and the control function, the control part of which is easier, but the perception and response part is which is the harder part to maintain for autonomy. So we geared our efforts. My work is R&D, is not really in industry, but mostly research and development. So we focused our work on cooperative mobile robots or autonomous cars, on the issues of sensors, localizations, trajectory following, communication between these robots, and cooperation between them, and hierarchical control. Also, because we have always driver issues, the handoff between autonomous driving to drivers, we focus on various aspects of physiological measurements of the driver condition, therefore being able to understand in what state is the driver, when is the appropriate time to transfer control to the driver, or if doing that at all. One of the areas that is very popular and proven to create efficiencies is cooperation between vehicles and communication between vehicles, which produces the capabilities of efficiency, safety, in truck efficiency, for example, truck platooning has shown that you can save the gas economy by almost 20% if you use platoon, depending on the size of the platoons and the miles traveled. So we worked on the coordination of the vehicles together. How do you communicate? How do you control the vehicles all together? And how do you form these platoons? And merging of these platoons with different control technologies is one area that is one area of R&D that we pursued. In order to create a test bed for things rather than going to the field test, which is very time-consuming, very expensive, we developed a mobile robot-based laboratory which has all the elements of an autonomous driving, from GPS to IMU to camera to communication between vehicles. So this platform allows us to test things quickly before moving on to the real vehicle size. One of the areas, this is just an example of control system design for connected vehicles, where we actually use the information from acceleration of the vehicle ahead as a feed forward in the control, which is that F block that you see that's coming from the vehicle from front, and the vehicle in the back has a controller that controls the distance or time gap between the two. So we worked on these and showed that actually adaptive cruise control or automated cruise control versus cooperative adaptive cruise control will add benefits. So if you look at the errors on the bottom on the left-hand side, it is the time gap using ACC. If you look on the right-hand side, is CACC, which is cooperative adaptive control, which reduces the time gap, therefore providing better performance for collaboration between these vehicles together. So I'll let this drive a little bit. These are just for demonstration purposes. They're not, obviously not real vehicle, but just to test our algorithms and make sure that they work properly. So CACC maintains a better control of the driving. Another area that we worked on is really integrating the sensory and the computational capabilities within the vehicle along with communications when a sensor itself fails. So if the sensor, in the absence of the sensor corrected data, when you have only communication, can you do the car following or not? And that these are trying to address the realistic situations that may happen, or maybe the sensor will be blocked, or there is fog and the vision doesn't work. How do you keep controlling the vehicles in a coordinated manner? So again, it shows, the results here show that you can, in the case of failure of the sensors, using communications, even though you have delay in the communications, you can still maintain the time gap, the desired time gap within certain boundaries. Another area is where you want to maintain the trajectory of the vehicles that are following each other, not necessarily in the absence of the sensor, where the sensor field of view is not sufficient to create a car following, a trajectory following situation. So in this system, we have a different control system that, again, uses the same technology, communication between vehicles, and communication enabled us to create the trajectory following that were desirable. Now, there are different things come into picture here. The red lines or the red dots are the trajectory that you want to follow, which is the center of the lane, but your localization results are shown by the triangles, and the squares are the GPS, so they're not necessarily in the same point. So your calculation versus what the GPS is giving you is not necessarily identical. Therefore, you have to have an algorithm that allows you to do the proper following. We have tested these in a laboratory. This is a top view of the track that the two vehicles were traversing. The left-hand side is the lead vehicle, the blue line is the lead vehicle trajectory, and the right-hand side, the black lines are the follower vehicle trajectory. Again, this shows that when you go around the curve where the sensor fails or the sensor is not available, communication keeps the control of the two vehicles together. So again, these are laboratory tests to show the feasibility of the things. Of course, these work in an autonomous mode where they do lane keeping, the center of the lane, car following, and all the other things. So we test them in the slow mode, and then we test them in the higher speed and going around. So in the interest of time, I probably will stop that. This will go around that circle that I showed, or that square that I showed, to just demonstrate that the robots or the autonomous cars can indeed follow each other in a coordinated manner and maintaining the time gap that is desired. The data shows that the trajectory following that was desired is actually accomplished. So, and it shows in the upper plot on the right-hand side that where the black lines are, where they miss the black lines, that means some of the information is missing. That means you're around the curve. And when you're around the curve, it goes back and forth. That means this has an algorithm that looks at the sensor data, uses the sensor data for trajectory following. When the sensor data is missing, it relies on communication to follow the vehicle ahead. So we can maintain platoon in all conditions. Now, obviously, you would know that the current vehicles, the vehicles of the future, have a variety of sensors. My colleague will talk about LiDAR and other sensors that their company provide, but there's also video camera, mid-range radar, and long-range radar. So collectively, they provide a sensory field around the vehicle that will give you all the situational awareness that you need to create autonomy. Now, these are all the elements, without getting into details of those, the elements that you need for autonomous driving is just a simplified block diagram. Ultimately, what you want to know is what happens around the vehicle, what signals are coming from other vehicles and infrastructure, how to define your trajectory, and how to follow, which is the actions that you create, the control actions that you create for steering, throttle, and braking. So we don't have time to get into too much details on these things, but the list of required enabling technologies I thought may be useful to this community is in one of our publications and books. So I believe that if you have these 9 capabilities, then you have autonomous capabilities of today's vehicles. One, the first is to be able to estimate the state of the vehicle itself. Second is all your external sensors that I showed in the previous slide, which creates a situational awareness and estimation of all your surrounding data. Then you have global and local maps and information and GPS and what have you that shows where you are in the bigger picture and the map. You would need wireless communications if you want to resort to communications and interactions between vehicles and pedestrians and etc. You need a knowledge and estimation of the driver state if you want to be able to hands-off control to the driver. And you have to have a multi-level sensory and data fusion and situational awareness capability, because without that, you may be missing some of the information that's provided to the vehicle. You need ultimately an AI-type controller, because deterministic models will give you the car following and trajectories of that nature, but you do need learning capabilities, because the most difficult situations are where the situations that you have not encountered before, or based on the experience of the driver, which in this case would be based on the experience of the AI system. You want to have a proper interface with the driver and generate warning alerts in case you're transferring control to the driver. And finally, you have to have a cooperative perception capability. That means you not only have your own sensory capabilities, but you also have the sensory capabilities of other vehicles providing information to you. I think with these 9 comprehensive systems in place, you have a full autonomy and the ability to reduce fatalities or accidents altogether. I have another example of what we did with cooperative perception is when one vehicle actually provides information to another vehicle for collision avoidance. And we tested this system in a variety of situations. The key element in cooperative perception is that 2 or more vehicles, actually the first part of it is relative pose estimation. That means you have to know where you stand or what your field of view is relative to others. In order to do that, you need to have a common feature in the view ahead, and that common feature allows you to do triangulation. So with that, then you detect and localize the object, and then you can transfer the information. So you can imagine situations where the red car is giving message to the white car to know of forthcoming obstacles. So in this situation, one vehicle is providing sensory information to other. That's why we call it cooperative perception. Now, extension of this is very difficult if you have multiple vehicles. Those are very complex, both geometrically complex, but algorithmically very complex problems to solve too. So we created a whole bunch of test scenarios and we tested our system on that. This is just a simplified system again with the robots that shows without this cooperative perception and with cooperative perception how your system can handle the situation, the sensory situation that's prevented. That was on the left-hand side, the top view of going over a, let's say, hypothetical pedestrian. Dramatic. But on the right-hand side, the system has cooperative perception, so one robot actually transfers the data or communicates data to the other one. The blocks that you see are part of the localization scheme there, and in this case, the ego vehicle does not actually recognizes the obstacle in front from the other vehicle and stops. So these are obviously proof of concept, not executed on larger vehicle, but we have a lot of test beds on the larger vehicle that we are developing. And in this way, the previous case, you see how the robot on the right actually run over the pedestrian. In this case, it doesn't. So it shows that actually the system works. The communication can enable the blocking of the collision. Now, that we have a number of test beds in our university, in our department. Part of the Auto Drive, which is a GM and SAE student competition on the upper right. That's our team that won third place. The one on the left is from 10 years ago, the DARPA Urban Challenge. And currently we have 2 other autonomous vehicles that we are working on to expand our autonomous test bed capabilities. I want to shift gear from here and then do a few more, maybe 5 more minutes on something that I think is very important to know. And I think this is the way of the future. If you look at the data on the growth of the number of vehicles worldwide, you would see that there's enormous growth of number of vehicles sold. And I think in the next 2 decades, which means by roughly 2030 and above, the vehicle ownership is expected to double worldwide. So the numbers are staggering. Like 2 billion cars will be driving on the roads. Now, is this situation sustainable with the current size of the vehicle and accident statistics that I've shown earlier, and even the traffic congestion that you would see? So you would see that it's just impossible to have this many cars on the road without the introduction of new technologies. But let's look at historically how we created mobility for ourselves. So bear with me here as I go through this history. So this is where we were. This was our mode of transport, either walking or horses or camels or other animals. Then we created a carriage to create comfort for that. Then we added to the numbers and made them bigger. Then we created a traffic situation with carriages. Then we went on and created the first cars. Then that wasn't enough, so we made them bigger, more powerful. That wasn't enough, we put turbo engines and stronger engines on them, so we got like 300-400 horsepower on them. Then we made them more slick and faster. Then we made them bigger because we needed more room, or we like bigger, more powerful things. Then we made them even bigger. So what's wrong with this picture? This large car that you see on the lower right corner, a lot of times it's just carrying one person. 4,000 or 5,000 pounds of steel carrying and 150-pound person or 200-pound person with the luggage. So there is something wrong with this engineering picture that what we are doing. So this is why the accidents are happening. This is why the congestions are happening. We did some things right, so we're moving towards electric vehicles and maybe more efficient vehicles. But what we have done is we have a very large system. This is one of the I think this is one of the biggest mistakes in engineering we made if you compare to any other engineered systems. The vehicle is really, the direction that the vehicle growth has gone is the wrong direction. We created traffic complexity, we tried to solve the traffic problem. We created significantly increased power, then we tried to mitigate death and injuries due to that power. We created serious environmental challenges, and we tried to mitigate that by process design. We created excessive energy consumption, we're trying to go to hybrid systems. We created excessive use of steel and metals, and we tried to do recycling to compensate for that. All in all, I think the direction, the way the automotive technology has gone is the wrong direction. So what is the future? Is the smaller cars, individual mobility, and I'm very glad that I saw one of the companies in India is actually working extensively on that, and Mahindra had the example on the floor, which was very promising. So smaller cars, individual mobility, or one or two people moving is, I think, the way of the future. If you look 20 years down the line, it's impossible to have the cars the way we have currently to go within the traffics of any of the big cities. Imagine Mumbai, Shanghai, New York City, Los Angeles, etc. So if you want to go from point A to point B, the current vehicle is not the situation. So you go and compare all the other things that are out there, you see that at least some of the vehicles that are going in the right directions with the smaller power, smaller footprint, and much more efficiency can do the same job. This is for ride sharing, for going from point A to point B, and a lot of other details that I can't get into right now. But by just sheer example of reduced size, you can see that you can quadruple, if not triple, the capacity of roadways. There is nothing else in intelligence and communications that you can do to be able to provide this kind of efficiency. So I really think the way of the future is single vehicle, individual people movers. Now, I know my time is out, so I'll be very quick. The final general remarks towards autonomy, mobility, and safety is that our focus should be on sustainable mobility solutions, lighter weights, electric and hybrid, create uniformity and compatibility to create safety. Combined ADAS and autonomy is expected for foreseeable future. You will have a mixed and autonomous and manual driving, so a lot of the things that I've shown we really need to work on to ensure safety. Autonomy challenges are mostly in perception, fusion, and critical decisions. Actuation and control issues are important under extreme conditions only. The regular conditions are kind of redundant and are solved. Both safety and traffic solutions will heavily rely on connectivity because it's only the benefits of the autonomy comes when we create that connectivity. And the requirement for all of them are integrated solutions that are robust and reliable. With that, I thank you for your attention. I'm sorry I ran my time a little longer than expected, and ready for any questions, I think, later during the panel. Thank you very much.
Thanks, Azim, for the excellent presentation. I'm sure there are a lot of questions for you, and you did give us some glimpse of the use cases in terms of perception and in terms of the response of various vehicles, and also talked about shared mobility, asset lighting, and so I'm sure the audience will have a lot of questions. So we'll come back to you later. Now I'll request Dr. Gopalan to come and make his presentation.
Well, good afternoon. Azim had a challenge of starting immediately after lunch. I think I have a slightly bigger challenge of standing between you and your afternoon tea or coffee. So I'll do my best to make it worth your while. Still don't see the slides. We joked that we thought we had all the AV system worked out, but it's inevitable. That has to happen, right? Murphy's Law. Well, let me get started by just introducing myself again. My name is Anand Gopalan. I'm Chief Technology Officer of a company called Velodyne Lidar. So for those of you who may not be familiar, and a lot of people in this audience may not be familiar with what Velodyne does. Yeah, there you go. Okay. Yep, so I think we're good to go. So again, for those of you who are not familiar with what Velodyne does, we are the premier LiDAR sensor provider in the world today. So we provide sensor solutions into most, if not all, autonomous and ADAS programs in the world. We have 70 plus independent programs spanning the globe, working with all major OEMs, with maybe one or two notable exceptions, who are working on autonomy and ADAS. So this gives Velodyne, and particularly me, a sort of bird's eye view of what's happening in the mobility, autonomous mobility space and advanced safety space, which I hope to share with you as part of this talk. And then I will also try to give you some pointers from my opinion on the context from an India perspective. So I'll start by just going over a brief history of autonomy, and really from a for Velodyne, the history of autonomy is tied in very closely to the history of Lidar as a sensor and Velodyne as a company, which will take us to where autonomy is today. And then I will talk a little bit about sensor challenges, because that's near and dear to our hearts as a sensor provider. And then we'll talk a little bit about the India context. So this is what started it all, at least in the modern sense of autonomy. Azim mentioned it briefly. It's what is known as the DARPA Grand Challenge. How many people in this room are familiar with the story of the DARPA Grand Challenge? There's a few hands. So DARPA, for those of you who don't know, is the US equivalent of DRDO. They're a research funding organization tied into the Department of Defense in the US. And in 2004, DARPA came up with this challenge which said, you must build a vehicle that drives itself independently in the desert. And several teams participated in this. I think Virginia Tech was there, Stanford, Carnegie Mellon. David Hall, who's the founder of Velodyne, participated as a private individual. And everyone failed. None of the vehicles were able to actually succeed in the challenge. So David, in this case, went back and thought about the problem, and then realized that the problem was a perception problem. So in his words, he could see all of the road some of the time, or see some of the road all of the time, but he could never see all of the road all of the time. And so this led to the development of 3D Lidar, which I will talk about in a little bit. So lo and behold, David went back, and DARPA reopened the challenge, except they mandated that David couldn't be part of the challenge because he would have an unfair advantage. And so he supplied Lidar to a majority of the teams who were in the challenge. And so the urban challenge, which happened in 2007, was the first time that teams finished an autonomous driving challenge. So 6 teams finished, 5 of them had Lidar. In fact, they had David's Lidar on them. So what you see in the video is the first Lidar, and that's I hope you understand that's not how Lidar looks today, but that's what it was in those days, a big wheel on top of the vehicle. The road to autonomy is not a road, something that started this decade, of course, right? Here's a 1925 newspaper article that talks about an autonomous vehicle. So the concept of autonomy is almost as old as the concept of the automobile. And it's been a long road, ever since the invention of cruise control, which happened in the 40s or the early 50s. We have taken a meandering path towards adding successive features of some type of autonomy, cruise control being a large portion of it. 2007, after the DARPA Grand Challenge, a lot of the people who were part of that spread out and joined a lot of the companies who are working on mobility, autonomous mobility even today. So Google and Ford and GM and so on, all were seeded by these people who worked on the Grand Challenge. The first thing that people realized was that the sensor that called the Lidar was able to really map the world very accurately. And so immediately this started the race to map the developed world. And so Google, today if you take your phone and look at any Google map, it's likely that it was actually developed using a Lidar sensor. Once you have a very high definition map, then maybe you can drive yourself through the map, and this is how this idea of autonomy got started. Which brings us to where we are today. So the question that I get asked pretty often is, when is an autonomous vehicle ever going to come on the road? When do you think that's going to happen? Any takers? The answer is today. Autonomous vehicles are on the roads today. They are used in very interesting and different business models. These are not consumer purchase vehicles. These are fleet-operated vehicles, but you will find autonomous vehicles on the road today. Of course, Waymo being the Google self-driving car arm is a famous one, but there's others here. These are robotaxis. These are autonomous shuttles. May Mobility is an example down there. There is Voyage on the extreme, your extreme left bottom, which is essentially an autonomous vehicle solution for aged people in aged homes, and it transports them to places that they need to go in a geofence location. But it's not just about cars. I think that's one key takeaway that I would like to present to you. We're seeing a paradigm shift even in the movement of commercial vehicles, which is something people loosely refer to as the Amazon effect, right? So past 2 decades were always about man to goods. So which means you had goods which were aggregated from many different places, and they were brought to a common location. It was a market, it was a supermarket in the case of the West, the Walmarts, the big bazaars, and so on. And then man would basically travel to this place and then pick up goods, whatever he needed, on demand from that Walmart or big bazaar. That's no longer true. Today, I want to be able to take my cell phone and pull up Flipkart or Amazon and order something and have it reach me the very next day or in 2 days. This has completely changed how goods need to move. First of all, this means that the good getting from its source to a warehouse near you has to be in a very flexible fashion, which has meant that trucks have taken over from trains in terms of the means to transport large volumes of goods. Further, from the warehouse, instead of going to a store, now you have 1,000 endpoints. You're going to 1,000 homes. And so this has, again, completely changed how delivery happens in the last mile. So where will you find problems in safety and autonomy? Just about everywhere in that chain. Because now you have truck drivers who need to drive significantly more amounts of hours a day to be able to get those goods to the warehouse. And then you have a proliferation of small vehicles delivering those goods to your home. And so in all of those situations, there is room for autonomy and there's room for advanced safety. So this is an example of a Peterbilt truck that was driven to be level 3 and level 4 autonomous. There's examples of other trucks that have driven across the US. This is an example of a last mile delivery vehicle which delivers groceries to your home and which runs autonomously. In places in Michigan, Ford runs this program where you can deliver pizza. You can order pizza and it'll get delivered to you in an autonomous vehicle. This is an example of that. Of course, China is not being left behind. You're seeing a huge proliferation of last mile delivery vehicles in the Chinese market, delivering goods to the curbside. This is an example of delivering food to your home, which is running in San Francisco today. So it's not just about you being able to buy a vehicle that drives itself autonomously. It's really about delivering goods in an autonomous and in a safe manner. So let's talk a little bit about sensors. The obvious question to ask is, why do you need LiDAR? I get asked this question all the time. Why not use a camera? So if you take a look at the visuals, I think they sort of explain for themselves why cameras don't work. Cameras work well in many conditions, but essentially they are dependent on ambient light, which makes it a challenge. And then it's almost impossible to use a 2-dimensional scanning system to figure out what's happening in a 3-dimensional world, as that video there demonstrates. And that's sort of how radar sees the world today. So what does LiDAR do? I mean, it's pretty simple, actually. All it is you send a pulse of light, and you measure the time that it takes for the pulse to come back, and that time essentially gives you distance. And that's pretty much what LiDAR is. Except we don't use visual light, we use near-infrared to achieve that. So what does this mean from a perception standpoint? So if you go back to this example of why you need 3 dimensions, so here's a very simple scenario. A person walks into a room. Here's what a 2-dimensional scanning system will look like a radar or even a 2-dimensional Lidar. Can anyone actually tell that that's a person walking in a room? It's almost impossible for a perception system to make out 3-dimensional information in a 3D world from a 2-dimensional scan. That's what a 3D LiDAR would show you instead, which is a completely rich 3-dimensional view of the situation. And by the way, because you're taking very accurate measurements of the environment, you can see that same scene from any perspective just by rotating and just transposing the coordinates. So how does this work in the context of an autonomous vehicle? Well, it all starts with a map. So most autonomous vehicles today either use a base map that was created, or they are creating a map as they are driving through the world. And this map is a high-definition map created usually using some form of LiDAR. And this is able to map the various key parameters of the road around you, which is curbs, lane markings, signs, vertical clearances, and so on. So the autonomous vehicle is actually not driving in its sense in the real world. It's actually driving in its own high-definition map. And the more rich and accurate that map is, the more accurate that the vehicle will be able to drive itself through this world. So if you put all this together, since we are short of time, I'm going to jump to the final answer and say, how is autonomy accomplished today from a technology perspective? So it starts with, in this case, a LiDAR point cloud. You then take out all the things in the environment that you know are not that are not the driving road surface. You're trying to establish what is your static road surface. You do this by segmenting the world in terms of height, and then figuring out where your actual road surface is and where the curbs are. You then also go and you add reflectance data, which then gives you where the line markings on the road are. So where are the lanes, where are the signs? And you're creating a fairly high-definition map at this point of the world that you're driving through. And you're doing all of this real time. So these are all real-time algorithms that are used. You're figuring out where the curbs are, as an example. Then once you have that, you can now start tracking the dynamic objects in the scene. So we just threw in all the cars that were driving around the car in question. And you start being able to look at these cars and identify them as not being static. The blue boxes now show you all the things that the algorithm thought were dynamic, and they are now being tracked, with all the red boxes being rejected as static objects. Then you can actually classify it. So if you could actually look very closely, it would say van, pedestrian, car, and it would give you the velocity of those objects in the scene. So now you have created a dynamic and a static view which can then be merged, and now this is the rich view that an autonomous vehicle sees as it drives through the world and makes decisions on where it needs to drive. So this is current state of the technology from a perception perspective of how autonomy is accomplished today. You can see an example of a fairly crowded intersection with several vehicles, which are all being tracked by the algorithm. So LiDAR is not the only sensor in the picture, and I must say that LiDAR is not the only sensor that's used. So you have radar and camera, which are actively used in conjunction with LiDAR. And there is room for all 3 sensors because they meet different requirements, as is shown by this chart. And I won't go into details, but there's reasons to actually have all 3. And so autonomous vehicles will see, as Azim said, a combination of radar, LiDAR, and cameras on them. Sensors are pretty powerful today. And here's an example of what a LiDAR sensor can see. So this is, again, running real time on a vehicle stopped at an intersection. And you can essentially see the world 300 meters around the vehicle. So you're able to see the entire intersection, vehicles passing the intersection. You're going past the vehicle to be able to see the building on the other side of the intersection. You can see as the vehicle drives through a very dense neighborhood with trees, you can still make out the road signs, you can make out parked cars, you can see a pedestrian who's trying to cross the street, and so on. So LiDAR as a sensor, and it's not the only sensor, every sensor is getting more and more powerful to be able to create a rich real-time perception of the world today around you. And sensors are getting smaller as well. So you saw the wheel on top of the original truck 10 years ago, and that's the size of our latest LiDAR. And as you can see, sensors have gotten really small, and when they get small, by the way, they also get cheaper. And so definitely you're seeing the economies of scale being applied to all the sensors used in autonomy today. So this is where we are today. We are on the left of that chart. We are at safety. We are trying to establish the safety case in the developed world. Then people will talk about power, and then they'll talk about cost. Of course, in India, people usually talk about cost first. And so really, there is a question of how this technology will get applied in the Indian context. So I showed you a really nice picture of an intersection with 5 cars. And I'm sure a lot of people are saying, that's not how an intersection in India looks. This is how an intersection in India looks. And is this technology ever going to be applicable to the problems that we are trying to solve? So whenever I talk to people in the conference, there's 2 things that I've heard. One is, the Indian problem is too complex to solve from a technology perspective, and then there isn't a clear business case to be made. And I think both of those have some validity, but I can give you a few thoughts on where I think why we need to work on this. So Azim already mentioned this. This is a really important statistic for us, all of us in the industry, to keep in mind. 1.3 million deaths a year. The only things that exceed that as single causes are cancer, diabetes, and heart disease. So really puts in context what we can achieve by trying to make our vehicles safer, even if they're not fully autonomous. So safety and autonomy, in my mind, are two parts of the same coin. All the technologies that I talked about equally apply to making a vehicle safer and to advance safety as much as they apply to autonomy. So here's the SAE levels, which Azim also talked about. And I think the point I want to make here, without again going into the details, is you can make a vehicle significantly safer if you achieve level 2 autonomy, which does not take the driver out of the equation whatsoever. And not only for passenger vehicles, but more importantly for commercial vehicles, because these commercial vehicles, as we just talked about, are multiplying and are facing increasing challenges in the world of goods to man because of things like Amazon and Flipkart. I think there's a need for a beachhead of applications that will start the ball rolling in the Indian context. So here, my humble opinion simply are commercial vehicles like trucks and buses, where how many days goes by before you read of a truck accident or a bus accident that killed several people in an Indian newspaper. So imagine being able to, again, make these significantly safer, not necessarily taking the driver out of the equation, but adding levels of autonomy that allow the vehicle to safely pilot it when the driver is distracted or incapacitated or unable to pilot the vehicle correctly. Another interesting area that seems to be an area of work is agriculture, and there's lots of interesting autonomous solutions that could be developed in agriculture and other industries like that. Mining is another one which has been an area of active work. So I'll end with a few comments from on the Indian context. So first and foremost, I believe that full autonomy, while it makes sense in the developed world, is not the only solution for all markets. In the Indian context, it may make more sense to go from level 1 to level 3 first, and that could bring huge value to citizenry, to safety on the roads. Similarly, on the commercial side, level 1, level 2 vehicles which assist the driver in piloting his commercial vehicle safely could be hugely valuable. We should not forget that for many business and commercial reasons, which maybe we'll get into in the discussion, the rest of the world is moving towards level 4, level 5 autonomy. And if India is a big stakeholder in the global autonomous market, we must be developing solutions for the global market, which means level 4 and level 5 from a solution perspective should not be off the table in the Indian context for engineering firms working in India. in my opinion, technology does not change in a linear fashion or even in a non-linear, smooth fashion. Technology changes in quantum leaps. And whenever you have a quantum leap, it's actually an opportunity to not only be able to catch up, but sometimes take the lead in technology. And I believe that autonomy and advanced safety is one such opportunity for the Indian automotive industry to be able to contribute in a major fashion to the world. So I'll leave you with this thought. All the forces in the world are not as powerful as an idea whose time has come. And the idea of advanced safety and autonomy is going to be the idea of the next decade. And I think the people in this room in the Indian automotive industry are well equipped to develop technology and solutions that not only improve safety for their own citizenry, but for the world at large. Thank you.
Thank you, Dr. Gopalan, for an excellent presentation. Definitely touched the Indian context, and that was heartening to see. And your point about solutions which are existing and looking at people jumping onto the bandwagon just because that's a technology which is available is something I think we should all look at. And data, I always believe that data interpretation and understanding of data is very important before we get into the technology choices. So thank you very much for an excellent presentation. So we have some time, maybe 5 minutes for some Q&A if there are any questions for the panelists. Please raise your hand and then we'll get you a mic. Can you get a mic to the gentleman there?
Hello. Very interesting presentations. But typically, in Indian context, we always are caught up with cost, as rightly pointed out. And if you see the data analysis, you'll find more often than not, a lot of accidents happening in the wee hours in the morning or late at 1 o'clock in the late night or 4 o'clock in the morning. Many very fatal accidents do happen. And sometimes we also confess we can't always afford a very high level of automation. I thought if there's something like semi-automatic, like, I'm a bus driver, and will I like to have something which wakes me up or which kinds of alarm me late in the night or while I'm driving in the early morning in expressway? Because there's some thought, like you talk of level 4, level 5, somewhere in between, like even the man is sitting on the steering, but I get the assistance. Hey, you wake up or you be alert or something is happening, your vehicle is drifting or some odd vehicle is coming in front of you. If something, that kind of solution which can be kind of retrofitted, we Indians love this word called retrofitment. And a normal car, I would like to make it semi-automatic and then automatic. Is there any solution in between which will save a lot of accidents?
This question is addressed to Azim or?
I think both.
Both?
Anand,
Okay.
More on the Anand side.
Anand, okay. Right.
Okay, this mic's working. Okay. Actually, that's the approach that a lot of truck OEMs are taking. Because I think the investment in a truck, especially that's already on the vehicle and the fleet, is pretty high. So trying to just scrap a fleet and build new trucks does not make any sense, even from a commercial perspective. So even in the developed world, and it's the examples I showed you of trucks like Peterbilt were all retrofitted. So, and also to your point, these are not even though they may be sometimes capable of level 4, these are often meant to be level 2 systems and maybe level 3 systems. And you can have a debate about whether level 3 is actually even safe, because level 3 expects the driver to somehow take control in a bad situation. But these are definitely level 2 capable systems. The other thing that goes in hand with what I talked about is driver monitoring. And there's a whole slew of solutions out there which are also actively monitoring the driver for tiredness, for distraction and so on, which will then kick in the level 2/level 3 system. So yes, you're absolutely right, and that's the approach that a lot of the truck OEMs worldwide are taking.
Thank you very much. Just to introduce, I make 3-wheelers from Hyderabad. Thank you very much.
Nice to meet you.
Thank you. Anybody else? Any questions? I have a question for you. You mentioned about road surface and mapping the data. So in India, we have a very typical issue of speed breakers which come up. So any thoughts on that?
Yeah, so there's speed breakers. Yeah, yeah. So those are, I mean, handled fairly well, actually. I mean, you do have speed breakers in the West as well. I think the key thing is, at least the solutions that we work on, which are LiDAR-based solutions, you are deriving depth information, three-dimensional information. So even if you don't have lane markings, you will be able to detect the side of the road because of some changes in depth. Similarly, you'll be able to detect speed bumps as well, or speed breakers. So that's definitely, I would call it a solved problem.
Yeah. How about undefined objects which are very prevalent in the Indian roads?
I'll let Azim jump in.
One of the items I mentioned on the list of 9 technologies was a learning algorithm. I think one of the basic challenges in object detection is whether, for example, if you have an empty box, is that an object or not? Is that something you have to avoid or go through another danger to avoid or not? But learning algorithms are supposed to answer these questions that based on the experience and miles traveled, you learn from experiences just like a human learns from those experiences. Now, one of the areas to address your previous question is we are working on is what is the drivable surface or what is the drivable area, specifically for areas where lane markings or even at the intersection where there is no guidance for the vehicle. But you look and work on algorithms that are based, vision-based in this case, that identify the drivable areas first, and then there are probability models for collision and collision avoidance that you need to consider as well, because nothing is in real life is 100% deterministic. So you have to take into consideration the trajectory of other objects or other vehicles coming into your drivable zone and the probability of them being in your drivable zone. So the problem from a mathematical perspective or engineering perspective does get very complicated, but I think there are solutions on the horizon. It's solvable.
Solvable,
Yeah, right.
thank you. So we have, yeah, Murli. Can you get a mic?
My question is to either of you two gentlemen. One of the issues that we are at SAE International encountering is the issue of liabilities on part of the manufacturers. When the vehicle is semi-automatic or complete autonomous, where does the blame go on in case of a failure, particularly in case of a major fatality? The OEM pays for it, the driver pays for it, who pays for it? There is a damage, there is a loss of human life. The liability issues are very important. So the insurance, the government regulations, OEMs, all kinds of challenges all come in the picture. What are your thoughts on that?
That's a difficult question. I don't think there is a solved, I don't think that is solved. It's solvable, but I don't think that is solved. I think people are grappling with this, definitely are grappling with it actively, all the way from the insurance industry themselves, all the way to government and regulations and so on. The one comment I would make is, again, as a result of having all this perception in the vehicle, actually the traceability of what happened becomes much, much easier. Because essentially you can reconstruct the entire crash based on, by the vehicle, with the data that's stored in the vehicle. You know, the examples that I gave, you're getting such a rich view of what's happening. So that's the good news, I would say. Definitely when you go from level 3 and beyond, the liability becomes murky, and there's definitely a lot of work. Ultimately, people think that there will be a model where, you know, the OEM has a certain level of liability associated with anything that happens in autonomous mode, but obviously that's not something that has been completely solved yet. Which is why I think fleets are the way that you're seeing this first being deployed, because the fleet is completely in the control of the OEM, and it's not a consumer purchase vehicle.
It's an excellent question. I think it is unsolved problem right now, but I believe just like any other technology, as we progress into this era of autonomy, there would be additional standards coming up that currently do not exist. And these standards go beyond OEM. They may go to the sub-level and the component level for individual sensor companies or actuator companies, and then each one of them will have a standard just like the other FMVSS standards are there. Like on crash worthiness, you're testing a vehicle that is based on measuring a force on the dummy on a specific test. That is not necessarily every scenario that would happen out in real life, but that test is a standard and the OEMs have to pass that test. So I foresee a future where Velodyne or other sensor technologies are given a specification that if their sensors have that level of reliability and that level of resolution that is required of them, then they are, they are not liable for the accident or for whatever the outcome of their work is. Of course, it is a very complex system at that point, at level 4 and 5, 3, 4, 5, because it's not a single sensor, it's multiple sensors, and it's an algorithm that needs to be tested as well. But I foresee that there would be even guidance for algorithms of that nature. A simple example is this: if you have a maneuvering and if you initiate a maneuver to avoid an obstacle, but you hit another obstacle which is in mix with manual driving. Now, who is at fault there? Whether you should have done the first obstacle or the second maneuver that you chose. So the situations can get very complex, but I think as we move along by developing systems, the standards for those systems will answer this question.
So thank you very much, gentlemen. I think we had a very good session today. Thank you very much. This is an idea which time has come, and definitely I think India is in a unique position. We need to find solutions very relevant for India. Of course, definitely the other side, we need to look at cost first, and but then technology is available. There are solutions which are available. Also, the technology is developing, and most likely the costs are also going to come down. And so therefore, I think ADAS is something which is going to happen. The government is also looking at that, and ESC as well as AEB is on the radar as far as government regulation is concerned. And this is going to be maybe notified maybe 22, 23. So quite quickly, even though Europe has still not done it, but that's something which is an idea which is there in the government. So I think it's a very useful session which we had from both of you. Both the gentlemen are available, I guess, after this session too, to answer any questions from the audience. And so thank you very much, and now I'll hand it over to the rapporteur.
Thank you, Raman San, and for both the speakers for the wonderful presentation. May I request the chairman of the session, Mr. V Raman, Senior Executive Director, to present the mementos to our speakers. Dr. Azim Eskandarian, Virginia Tech USA, on for autonomous mobility. I also request him to present memento to Dr. Anand Gopalan, Chief Technology Officer, Velodyne Lidar. And I request the organizing committee chairman, Mr. N. Balasubramaniam, to be on the dais to present memento to our chairman of this session, Mr. V Raman. Thank you all.